Okay, so we'll be discussing wind bridge oscillator. So basically, this wind bridge oscillator is an audio frequency oscillator, and you know that there will be two amplifier which we are going to use in the forward path. Suppose if you want to design any oscillator, then you need to satisfy two criteria of the Barkha-Hussein. The first criteria is mod of A beta will be equals to 1, and the second criteria is the angle of forward path gain and the feedback path gain should be equal to 0 degree or 360 degree. Fine. So now in this case, the common emitter amplifier will be used, and in the common emitter amplifier, the output signal is always 180 degree phase shift with respect to the input signal. Now you can see here the output signal is 180 degree phase shifted. Similarly, this is also a 180 degree phase shifted, 180 degree phase shifted. So already we have got 360 degree phase shifting of the input signal. So it means that feedback network should introduce a 0 degree phase shift, should introduce a 0 degree phase shift. So now how you are going to connect the wind bridge oscillator. So, okay, so for that okay, this is okay now. Now we'll come down. So this is wind bridge oscillator. Now you can simply, this is not a complicated circuit. This is a very simple circuit because you can see here this is the transistor. This is Q1 transistor, and to the Q1 transistor we have connected this R6. Now this is the thing. Then our to and to the upper one, this is plus VCC, fine. And you can see that the amplifiers are connected in the cascade form. Now similarly there are two transistors, because this is the first amplifier, this one is second amplifier. So the output of the first amplifier will be connected to the input of the second amplifier, fine. So this one is one resistor. You can see here this one is second. This is a voltage divider circuitry. This is a simple voltage divider circuitry. Voltage divider circuitry is here only. You can see this is the simple voltage divider circuitry. I think this is already discussed in the second chapter. And this is plus this is zero. So this is the same thing which we have drawn here. Now the output will be connected to a capacitor because we want only the AC signal. We don't want the DC signal, and this transistor is going to amplify both AC and DC. Suppose if you are going to use the biasing circuit, because in the biasing circuit, the operating point is located at the middle of the DC load line. So in that case, DC and AC both will be amplified. And if you want to block the DC signal, so you need to put a capacitor. So from the collector where you are going to get the both the signal, so DC will be blocked and it will pass the AC through it. So this will be connected here. So now this combination is going to introduce a 300-degree phase shift. Already 360-degree phase shift has been done. So now in the feedback path, you don't have to introduce a phase shift any. So that one will be, again you will have to connect a capacitor. See, capacitor is very much required because we don't want any DC signal to enter into the load. So now through the capacitor, we are going to sense a signal. Fine. To a capacitor, we are going to sense a signal. Now this one will be connected to some Wheatstone bridge type arrangement. I think this wing bridge is also has been completed in the EMI. This one is R1, then C1, then again this one is C2 and R2. This C1 R1 and C2 R2 is a lag lead compensation network. Is a lag lead compensation network. This is the galvanometer, which is going to tell us the null deflection, and this is the third arm. This one is the fourth arm, and this is grounded. Fine. So now I think we have not connected any resistance here. We have not connected any resistance here. So this one will be, I think, just a minute. This one will be connected. You can easily connect because ultimately we want a resistance that should be grounded. So I think this is the resistance which is grounded, na? So you can easily connect here. Fine. So this is the feedback network. But problem is that the you have used a capacitance, and capacitance will introduce some phase shift. Fine, capacitance will introduce a phase shift. This is a lead lag compensation network. I think this should be kept in mind. So now from where you will give the feedback signal, you can see that the feedback will be this part. It is a parallel combination of C2R2. Parallel combination of C2R2 will be given as the feedback. Circuit is very much simple. Fine. So now we will simplify the circuit and we'll try to obtain the frequency of the oscillation. I think we will right, we will have to select a frequency. We will have to select a resonant frequency. We will have to select a resonant frequency. I think this should be kept in mind that we will have to select a resonant frequency. At that time, your Xc will be equals to R. Now, what is Xc? It is the capacitive impedance of a capacitor. So by using this Wheatstone bridge, or you can say Wheatstone bridge arrangement, you will have to select a frequency, and at that frequency you will have to oscillate your output. So basically, at the you can say at this collector, you should have the resonant frequency. Now, how you are all going to obtain the resonant frequency? I think we'll come to that later. But before that, we will try to find the resonant frequency. So you can see there the output. Your output has been connected here. Fine. Your output has been connected here. So what I can draw, I think I will simplify the things for you. This is the output voltage. This is the output voltage. Now output has been given to which part? Output has been given to the this combination, that is the series combination. So this is what you can say, this is R1, then you are having a C1. Fine. And to this is given, you can see here the middle point, the middle voltage will be given to the what you can say, the feedback. Then this is R2, and this one is C2. Fine, this is okay. Okay, so I think we'll have to connect here, and this one is the feedback signal. I think the answer is clear to you now, because the voltage across the parallel combination of R2 and C2 will be given as a feedback to the input signal. Fine, input is not there. So I think this much is clear to you now. This much, and we will have to select a resonant frequency. And at resonant frequency, what is going to happen? The capacitive impedance will be equals to resistance. The capacitive impedance will be equals to resistance. Fine. Okay, so we'll move ahead now. Okay, I think the picture will be more clear in this diagram. The picture will be more clear in this diagram. So you can call this as the Z1. You can call this as the Z1 and this one as Z2. Now you can see here, this is the series combination, that is R1 plus 1 by C1s. So what is the value? 1 plus, if you solve the thing, that is 1 plus R1 C1 into S. I think it is very difficult to analyze the things in the time domain. So we have shifted our focus from time domain to a frequency, a domain. We'll do all the calculation there, because I think there in the S domain, you will be having only algebraic equations. Fine. So in that case, it is very easy to solve. Fine. Now similarly, Z2 will be equals to what? That is a parallel combination. So R2 into 1 by C2S and R2 plus 1 by. Now each and everything is in the impedance form. Now I think you take the LCM. So after taking the LCM, this one will be R2 C2S plus 1. Fine. So now what is the VF value? VF value means what? This is Z2 only. So Z2 into V0. Now here you will have to apply a voltage divider rule, because this much voltage is applied here also, that is across Z1 and Z2. So suppose if you want to calculate VF will be equal to apply a VDR, that is a voltage divider rule. So Z2 into V0 upon Z1 plus Z2. So now you can see here, if you just shift your V0 here, so VF upon V0 means what? Beta only, because I think in the closed loop system we have seen that this is VF and this one is V0, this is B, and from output you are, so VF upon V0 for this feedback circuit, output signal will be acting as the input signal. So VF upon V0 is the gain of the feedback circuit. Fine. I think this much is clear to you now. So now you just put down all the value. Just a minute. I will move ahead now. So beta will be equals to Z2 means what? It is now. Just put the values again. Z1 plus Z2. You do all the mathematics here. I think here you will have to take the LCM, that is C1s into 1 plus R2 into C2s. Do all the mathematics here. So I think some terms will be eliminated here. You can see here this numerator, that is this numerator one, and here this is common. So I think after doing the thing, so that will be reduced to R2 into C1. I think this will go in the upward direction. R2 into C1s, this one is the thing. So now R2 into C1s, okay. So now you just simplify the thing, because we have two square, we have two brackets, and I think you need to solve the bracket now. So 1 plus R2 into C2s, that is okay, this is there. So R1 into, I think this is there only now. So now what to do? We will have to put S will be equal to J omega. So for that, you will have to clear, I think you will have to free the numerator part. So this will come in the denominator. I think this will come in the denominator. So what is going to happen? You can see here, when R2 C1 will come in the denominator. So 1 upon R2 C1, you can see here, we have divided this entire term by this R2 into C1x, right? So this one will be same only, and this one will be what? If you just calculate, this one will be R1 upon R2, C1 and C1 will get cancelled up. Similarly, what is the thing? Right, this R2 into CS, R2 this is C2 upon C1, this R1, R1 C1, and I think one part will be eliminated. So you are going to have this value. Fine. So now you can see here what is the thing. Just a minute, I'll remove the. Okay, so now this is the value. Now put S will be equal to J omega. Now why you are not putting sigma? S will be equal to, why you are not putting sigma plus J omega? Because in this case you are going to have either the overdamped oscillation or the underdamped oscillation. We want a sustained oscillation, sustained oscillation. So for that you will have to put only J omega. J omega will give the constant oscillation. So I think where is the S value? That is J omega. This is at J omega, and you know that A beta is a real quantity. When you just put mod AB will be equals to 1, this A is real and B is real. So beta will not have any imaginary part. So we will put this imaginary part as 0. We will put this imaginary part as 0. So I think you will have to take it out separately. So you can see that we have taken this separately and we have taken this separately. Fine. Because beta should have only the real part, not the imaginary part. I think this is more clear to you now. So R1 C2 J omega, this one will go upward, minus J will go up, because in the denominator it is plus J. So in the numerator it will be minus J. So I think J will cancel, because J will be equal to under root minus 1. That will be having some significant value. So omega square will be equals to 1 upon R1, R2, C1, C2. Omega will be this. Now if you select the value in such a way that R1 will be equal to R2, you take R1 1 kilo ohm, R2 1 kilo ohm. Similarly, C1 and C2, you can easily select. So omega will be equal to 1 upon RC. F will be equals to 1 upon 2 RC. F will be equals to 1 upon. So this is the frequency of sustained oscillation for the Wien bridge, and this is the, what you can say. This is the resonant frequency. This is one is resonant frequency. So what you have done, you have taken the R1 C1 as the first term, then this is the C2 R2, the second term. It's a parallel combination. So basically, this arrangement has been done to select only the particular frequency, and that is the resonant frequency. I think this is much more clearer to you now. Okay. So now, what is the A beta? Okay, just have to put the values. Uh, okay, so beta will be equals to, okay, just a minute. Uh, Now A beta will be equals to what, for that? Before that, I think B will be equals to, I think this is 0. The imaginary value will be equal to 0, because this will have only the real part, C2 upon C1 plus 1. So B will be equals to what? So because we have selected R1 and R2 will be equal to R1 and R2 will be equal, and C1 and C2 are equal. So this will 1 plus 1 plus 1. So that one will be 1 by 3. So A 1 by 3. So B will be equals to 1 by 3. Now if you put the value A beta will be equal to 1 by 3, A will be equal to 1 by 3, 1, A will be equal to 3. So this is the value, that is amplifier gain value. Okay, so now why we have taken this R1 C1 and R2 C2, I think everyone will be having this question in their mind. So to quench your query and to provide you the solution, we will go upwards again. So now this, you can see this one is B input, and okay, so we have taken this as first arm, and this one is second arm. Now you can see that Xc will be equals to what? 1 upon 2 pi f is C. So at low frequency, you can see that at low frequency, what is going to happen? It is near to frequency is near to 0. At low frequency, this is not a zero frequency, but if you are considering at low frequency, so Xc will be equals to what? 1 by 0, that would be infinity. Fine. So what is going to happen? This one will be open circuited. This one will be open circuited, and you are not going to have any output signal. Why? Because this connection is open, no? So R1, and you will be having an open circuit. This is also R2. This one is open, so you are going to have this circuit, no? So there is no input will not arrive at the output. Now, similarly, at high frequency, what is going to happen? So 1 upon 2 pi f into C, f will be equal to infinity. F will be infinity. Xc will be 1 by infinity will be equal to 0. So in that case, now what is going to happen? R1, this one will be short circuited. This is R2, and this is short circuited. Fine. So this is short circuited. So again, this is short circuited means what? This R2 is a dummy element. Fine. So there is, you can see that there is no impedance. No. So impedance into current, that will be a zero value. So I think these are two extremes. These are two extremes which we are talking about. That is the low frequency and the high frequency. These are the two extremes. So you can see that this is low frequency and this one is high frequency. So between these two extremes, you are going to have the higher value, and that higher value is possible only when resonant frequency will be there, and that resonant frequency will be obtained only at Xc will be equals to R. Fine, Xc will be equals to R. Now similarly, you can see here there is a phase shifting. Fine. If you just calculate the impedance value, if you just calculate the impedance value, and if you obtain the phase, so what you are going to see that this for low frequency this is going to provide the positive, that is positive phase shift, and for high frequency this is going to provide a negative phase shift. Only at the resonant frequency you are going to have a zero phase shift, and that is why your feedback circuit state of the Windbridge oscillator introduces a zero phase shift. This is the condition, and this is the reason why we are going to use the series combination of R1 C1 and the parallel combination of R1 C1, and this will act as a feedback to your what you can say input signal. So this is all about the Windbridge oscillator. So in the next class, we'll try to understand the crystal oscillator. Thank you.